when you carry out fast Fourier transformation on this, it will be able to separate the forcing function that are superimposed into this kind of waveform that we are seeing into their respective frequency. Okay, that is what we are seeing on this frequency spectrum. So you are seeing frequencies at different levels. So these ones, they are very high frequency events, okay, which may be contributed by bearings. Are we getting it? Which is determined by the number of ball pass frequency, the number of balls times the rotational speed of the machine. Okay, we have both for inner race and for outer race. So which part that is called, if there's a dent in the inner race, there is a particular frequency that you will see such problem. If there is a dent in the outer race, there is also a particular frequency that you see such problem. If the bearing is cocked on the rotor or is loosed on the rotor, okay, all of this, you will see all of this information on different frequencies, okay, of the spectrum. So like we said before, as you carry out the fast Fourier transformation, you have something like this, okay. So 1 times the fundamental frequency, okay, 1 times RPM or 2 times RPM, we are seeing the peak. Then at higher frequencies, 10 to 20 times the fundamental frequencies, we are seeing different peaks. Are we getting it? So what are the things that are contributing all of these peaks, or what are the forcing functions, okay, that are contributing at these different frequency levels? Should be able to identify all of these. So when you're able to do it, then you will know, assuming this frequency now is a ball pass, assuming we have say 18 balls in the frequency assumption, then assuming this is a ball pass frequency now, which means that if this vibration level, or this gives you the magnitude of vibration as against the frequency order, okay, the number of harmonics, okay. So if it goes beyond the tolerable limit, then you will know that the bearing is actually getting bad. Okay, so this is the fast Fourier transformation. So like we said earlier, specific peaks, okay, as you can see on the spectrum, they correspond to specific machine faults, okay, and they are all related to the speed of the machine. That is the beauty of vibration analysis. So they will help you to identify these problems, and you're able to nip it at the bud before it will affect the integrity or the reliability of the electric motor system. So as we see here, imbalance. Okay, as you see here, imbalance, they will typically appear at 1 times RPM. So you see a peak like this. If it is 1 times RPM, that is as a result of imbalance. So imbalance, as we know, is when the center of mass, okay, does not coincide with the center of rotation or the center of gravity of the rotor, okay. So that would mean that we have imbalance on the rotor, and that will definitely increase the vibration of the electric motor. So that vibration, we will see them at 1 times, we see the peak at 1 times RPM once you have carried out your fast Fourier transformation, that is in this frequency spectrum. So if it is fan that is driven, the same thing. If the imbalance is on the fan, you also see it at 1 times RPM. So misalignment too, as you can see, you see it at the 1 or 2 times the turning speed, okay. So misalignment is when the center of each of the shafts does not coincide with the center of rotation of the shaft. So that is misalignment. So we have angular and offset misalignment. Okay, so the one on the left is the offset misalignment, and angular misalignment is on the right. So in most cases, you will not see just one type of misalignment. You see a combination of misalignment, both angular and offset. So it makes the situation to be complex, as you can see. So you see that we have an angular and offset. Okay, misalignment. This is what is common on in real life. Are we getting it? So this kind of misalignment, if it is in the system, you will see that in addition to the load, the motor will need to overcome that misalignment force, okay, around that coupling. So that misalignment force and the load that we are driving will mean that we will need more requirement on the electric motor system, which means that we will be overloading. We will giving the electric motor system or the electric motor itself more load than what we installed it for, because of that misalignment. And all of these increase in loading will affect the entire system. Remember, it will affect the heating of the motor. It will increase the load current, heating of the motor, and heating of all the electrical components, cabling and what have you, on the line to the point of input. Okay, so this misalignment, we can see it on the spectrum at 1 times or 2 times turning speed. So peaks at those two positions will tell us, but basically 2 times turning speed, okay, will show us the misalignment. And especially if we have that peak also on the axial direction. Are we getting it? That is a clear sign of misalignment. The looseness, when you have looseness, okay, you will see it at multiple peaks. There's multiple frequencies, the peaks at multiple frequencies. So when you have different and so many peaks, okay, on the spectrum, that clearly shows you that what you are looking at is looseness. So this could be taken care of by just tightening the hold down bolts and whatever bolts that is holding whatever part of the equipment. Are we getting it? So that's looseness. Then higher frequencies will give us idea about what is happening around the bearing. Remember, we talked about the ball pass frequencies, which is the number of balls times the RPM of the machine. Okay, so since we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 balls on this bearing, okay, so it means that information about this bearing will be seen around 11 times RPM, that is 11 times fundamental frequency, so which is around this area, okay, give us the bearing. Remember, we said the inner rays and the outer rays, okay, actually you will see them at different frequency levels also, but close around that 11 times RPM. Okay, so we can also see gearbox frequencies at those higher order harmonics, okay, or higher order frequencies. Okay, so gearbox vibration, I mean to say, you see them at the higher order frequencies. Are we getting it? Which is notably around the gear mesh frequency areas. Okay, there is number of teeth multiplied by number of teeth of this multiplied by the number of teeth of the other. That is the number of teeth of the meshing gears. Are we getting it? So if one has 10 and the other have 5, the meshing frequency is 10 times 5, which is 50. So vibrations, you will see them around those 50 and above. Okay, so the vibration analysis will help us to pinpoint the cause of the increase in vibration.